Dark matter and dark energy are the two greatest mysteries in science today. If anyone can solve either one of them, their achievement would rival Newton and Einstein. Why are they so important? We call all the visible things we see normal matter, but it only makes up 5% of the universe. The other 95% consists entirely of dark matter and dark energy. Let's start with dark matter. It is a theoretical, invisible substance in the universe. It doesn't emit light, it doesn't absorb light. Therefore, dark matter cannot be detected directly. So, here is the question. If we can't see it, how was it discovered? In 1933, astrophysicist Fritz Zwicky observed the Coma cluster. He noticed something strange. The galaxies within the cluster were moving far too fast. The gravity from their visible mass was not enough to hold them together. He concluded that a huge amount of hidden matter must exist. Its mass had to be over 100 times greater than the visible galaxies. Dark matter is invisible, but it has gravity just like normal matter. It influences how galaxies move. However, this bold conclusion was ignored by the academic world at the time. Key evidence later came from astronomer Vera Rubin. She studied the rotation curves of stars in the Andromeda galaxy. According to Einstein's general relativity and Newton's law of gravity, more mass means stronger gravity. As stars get further from the center, gravity weakens, and they should move slower. But the observation showed something else. Stars at the edge were moving much faster than predicted. At those speeds, the galaxy should have flown apart. Gravity alone, from visible stars, couldn't hold it together. Yet, the galaxies were perfectly stable. This was a very strange phenomenon. Think of it like a spinning top made of sand. You would need glue to keep the sand from flying off. Gravity is that glue. The galaxy is the spinning top. If only visible matter provided gravity, the galaxy would have collapsed long ago. This means galaxies must contain massive amounts of invisible matter. Its mass far exceeds the total mass of all visible stars. Since then, scientists have analyzed hundreds of galaxies. It's the same story every time. Even though we haven't seen dark matter, we know it exists because of how galaxies move. Vera Rubin's discovery changed everything. Scientists began to wonder, how do we find this stuff? Dark matter has mass. According to Einstein, massive objects warp space-time. Light bends when it passes through these warped areas. This is called gravitational lensing. By observing how light bends, scientists can find dark matter. It tells us exactly how much dark matter there is and where it is located. Using images from the Hubble Space Telescope, we can map its distribution. At first, some thought dark matter was just normal, non-luminous objects. Things like black holes, neutron stars, or old white dwarfs. These are called MACHOs, massive compact halo objects. But data showed these only account for a small fraction of the mass. Most of the matter is still missing. So, why can't we see it? Before this discovery, scientists thought everything was made of protons, neutrons, and neutrinos. But dark matter is different. It does not fit the standard model of particle physics. It has specific properties. First, it does not participate in electromagnetic interactions. That is why it doesn't glow. Second, it is highly stable. It has existed for the entire 13.8 billion years of the universe. Third, it moves very slowly. Because particle speed determines temperature, it is called cold dark matter. Fourth, Except for gravity, it barely affects normal matter. Every second, billions of dark matter particles pass through Earth. They hit almost nothing. This means dark matter is not any particle we already know. Physicists have many theories, but the most popular one is the WIMP model. WIMP stands for Weakly Interacting Massive Particles. The Sudan laboratory is located 800 meters underground. It was built in an abandoned iron mine from 1962. Teams from Fermilab use this space to hunt for dark matter. The core of their equipment is made of ultra-pure germanium crystals. A tiny thermometer is attached to the surface. The device stays near absolute zero. If a dark matter particle hits a nucleus, the temperature will rise slightly. Being 800 meters underground blocks out interference from other cosmic particles. There are dozens of these experiments worldwide. This includes the Jinping Underground Laboratory in China. So far, however, no particles have been caught. Another way to find it is to create it. CERN has the world's largest Large Hadron Collider. High-energy collisions might produce dark matter particles, but the chances are extremely low and hard to capture. So, scientists are also looking in space. Several missions are underway. These include the Alpha Magnetic Spectrometer on the ISS and China's Wukong Dampi satellite. Scientists guess that when two dark matter particles collide, they annihilate. By analyzing cosmic rays, we can look for traces of this annihilation. Dark matter remains a mystery for now. However, we have measured its scale. By observing the cosmic microwave background, we have the final numbers. Visible matter, the stuff that makes up stars and planets, is only 4.9% of the universe. Dark matter makes up 26.8%, and the remaining 68.3%? That is the even more mysterious dark energy.